Today we're going to look at Born-Haber cycles, and I'm going to show you how to use calculations to work out an lattice enthalpy. So quite often an exam question will give you a table of data, such as this one, and ask you to calculate an unknown value. And in this case, using a Born-Haber cycle, if we put all of this data in, we can calculate a lattice enthalpy. So the question might ask, calculates the lattice enthalpy of sodium chloride. And I've got all the data I need here. I've got atomization of sodium and chlorine. I've got electron affinity of chlorine. I've got formation enthalpy of sodium chloride, and I've got ionization energy of sodium. Now, I don't have to do lattice enthalpy here. We could actually have the value for lattice enthalpy in the table, and we could then be asked to calculate something else. But the method is still the same. The first thing I'm going to encourage you to do is make sure that you are drawing your arrows in the correct direction. Okay, so your arrows need to show two things. One, when you're drawing the cycle, make sure that you are drawing the arrow in the direction that the reaction goes. So, for example, the atomization enthalpy for both sodium and chlorine, you can see the reaction goes from the element in its standard state to the gas, element in standard state to the gas. So those two are going from the sodium to in solid to the gaseous sodium, from the chlorine in the gaseous state as half a mole of molecules to chlorine in the gaseous state as single atoms. And so the direction of the arrow is going to be important when you draw your Born-Haber cycle, but also whether it goes up or down is important. And because these are both plus, they are endothermic processes, we are going to draw our atomization arrows for our energy levels are going to go up. So that's starting with our elements in standard state. Let's put them in. Elements in standard state is always a good place to start. That's where I'd start. And so the first thing I'm going to do is I'm going to write out what the elements in the standard state are. Na, solid, and we're going to have half a mole of Cl2 as a gas. I'm going to write that out, making sure that I've got the balancing right. So 1 mole of sodium atoms compared to half a mole of chlorine molecules. And then, because we're going from that to that, and we know that that is positive, we can put, okay, I'll start with an arrow going up here. We can put delta AT H. It doesn't matter which one you're doing first. I'm going to do the sodium first and put that arrow there. Okay. We can that's representing that we are adding energy. It's plus. We're adding 100. We could put the number on there, 108 kilojoules per mole. More on that later. But we're going to need to do that. That takes us up to this level of energy. We're going to then do the same with the chlorine. We're going to go, okay, so the chlorine is going to be delta ATH for Cl. So on this line I had NaS, Na solid, and half Cl2G. So here what we've done is we've changed the sodium into sodium gas. So we're going to write that here. We're going to show the change, Nag. We haven't changed the chlorine yet, half Cl2 gas. So we're going to write that on there like that. The next thing we're going to do is we're going to go up to this level. And so what we've got now is we've got Nag, Na gas, and we've got now Cl gas as single atoms. So that's the atomization dealt with. The next stage is we've got the elements in the standard state have been turned into gaseous atoms. We need to turn them into gaseous ions. And the first thing I'm going to do here is go for the sodium first. Again, I'm going to do the ionization energy of sodium first. So that is the one at the bottom there. And that ionization energy is represented by this change. So we're changing Na gas into Na plus gas and electrons. So again, my ruler's out. We can see that this is going to be another plus number. We're going to go up to here. And we're going to just fill in what we've got at the top there as well. And you can drag this line across a little bit further. That means we have Na plus gas. We have now got an electron as well. And we still have the Cl gas atoms there. And I'm going to put my energy change on here. This is the delta IE H for Na, as it's written on here. That. Up we go. We've got to the highest level that we're going to get to in this example. And then we've got this, and the chlorine left over from over there. Now the chlorine is reacting with the electron. So this chlorine and this electron are going to react together, and that's going to make Cl minus. But if you look at the data here, that is the electron affinity. We've got minus 346. So minus 346 means we're going to go down. Put that over there for a minute. On this side. I'm going to put delta EA H for chlorine. And that's going to change us into, we've still got our sodium ion, Na plus gas. We've now put our electron onto the chlorine, so we've got Cl minus gas. Okay, and that is that change there. So our lattice enthalpy, we know, is going to be the joining of these two together, and we know that that's going to release a lot of energy. That is going to be delta LE H. And we don't have a value for that. We're going to need to calculate that. So I'll move the table over here a little bit. What else do we have that we haven't used? There we go. Delta F H, which is this equation. We're changing sodium, which is solid, and half a mole of gaseous chlorine molecules into NaCl. So that's going to be the enthalpy change of formation, which goes from here to the ionic lattice. And that is minus 411 again. So we can take out a ruler here, and we can find where this equation starts. So that is going to go here, delta F H, and that's going to be NaCl. That means that we've got NaCl solid down here. And that's our complete cycle. Now our lattice enthalpy, let's just check. The equation for that, remind ourselves, is Na plus Cl minus gas. Yep, goes to NaCl solid. So constructing our equation then, we said with the last video that if we take two different routes to the same start and end points, we end up with the same amount of energy overall. So if we take this route from here, and we go follow the arrow, 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 all the way around there, that should, from there to there, be the same as this, from here to here. So the best or easiest way to do this is delta FH equals, so from there to there, equals delta at of Na plus delta at of Cl plus, next one up, delta IE, oops, that's an H, Na plus delta Ea HCl plus delta Le. So having constructed our equation, we can plug in our values here. We've got minus 411 equals, atomization of this is 108. I'm going to put the plus here anyway, just to remind myself that I've thought about it. And then we're going to add the atomization of chlorine is 121. Then we're going to add the ionization energy of sodium, so that's plus 496. Then we're going to add the electron affinity, which is there. So that's plus minus 346. And then we're going to add delta LE H. And so you can see that what we're going to do now is we're going to we can do it anyway. We can sum this all up and then rearrange, or we can rearrange to start with. So the way that I'm going to do it in this particular case is sum it all up. And that means that when I take it off on this side and rearrange it, I get minus 379 minus 411 equals lattice enthalpy. And so if we add that up, we end up with minus 790 as our lattice enthalpy.